Alright, now we're going to prove some theorems about solvable groups. So let G be a solvable group. The first thing we're going to prove is that every subgroup of G is also solvable. So if H is a subgroup of G, then H is solvable. And our proof is going to rely on the fact that solvable groups have finite derived series. So what we're going to claim is that the ith derived subgroup of H is a subgroup of the ith derived subgroup of G. If that's true, then it immediately follows then that since G to the n is equal to 1 for some n, because G is a solvable group, then the same is true for H. H is also solvable. And more importantly, the derived length of any subgroup of G must be at most the derived length of G itself. So why should this claim be true? Well, let's use induction. The I plus first derived subgroup is the commutator subgroup of HI with itself. By the induction hypothesis, HI is a subgroup of G to the I. So we have this containment, but by definition that's the I plus first derived subgroup of G. Again, the thing that is missing, of course, is the base case. But of course, as mentioned before, why should that be true? Why does this even make sense? Because every commutator here involves elements that are also here. So every commutator in this set is a commutator in that set, and since this is the subgroup generated by these commutators, it must be a subgroup of this subgroup. So that proves this result. Notice trying to prove this result using the original definition of solvability would be pretty hard. You'd have a normal series for G, whose pairwise quotients are abelian, and you'd have to be trying to find a normal series for H. And there is actually a way to do it, but it takes a lot of effort to actually prove that it works. Namely, what would you have to do? If I remember correctly, you have to intersect each of the terms with H and prove that the resulting series is still a normal series, which you can do using one of the diamond isomorphism theorems. The harder part is proving that the resulting quotients are also abelian. It can be done, but you can see that all of a sudden you have to use a bunch of isomorphism theorems, whereas this proof just uses induction. Alright, the second theorem has to do with images and quotients. So suppose you have a group homomorphism between two groups, G and H. If G is solvable, then its image under the homomorphism is also solvable. A corollary of this is given any normal subgroup of G, if G is solvable, then the quotient group is also solvable. That corollary comes from taking the homomorphism from G to G mod n. And it's a surjective homomorphism, so its image is the whole group, quotient group. So here the strategy is going to be to show that the image of the ith derived subgroup is actually the ith derived subgroup of the image. So again, if G is solvable, there's some point where this is the trivial subgroup, and the image of the trivial subgroup has to be a trivial subgroup. Therefore, at some point, the nth derived subgroup of the image has to be trivial. And that's all you need. So why is this true? Well, again, one has to rely on induction. What are we looking at? We're looking at images of commutators. Where x and y are in the ith derived subgroup. Right? If I'm doing induction, I'm looking at I plus 1. So the image of this group is the image of the subgroup generated by these commutators. In some sense, that means you're looking at the subgroup generated by this image of the commutators. However, as we already saw previously, homomorphisms behave well with respect to commutators. So phi of the commutator is going to act this way. And so replacing x and y with phi of x and phi of y and doing substitution, we're looking at commutators of A and B, which are in this image, because phi of x and phi of y are in the image. And now by induction, we can replace the image of the ith derived subgroup with the ith derived subgroup of the image, keeping everything else the same. But the group generated by these commutators, as you range over this ith derived subgroup, is by definition the next derived subgroup. So we get equality. And so the book does it a slightly different manner. They're essentially doing the same thing, only they assume it's a surjective homomorphism. They call this group K. And so then they're calling this K to the I the whole time. But it's the same argument, and they do this forward direction and then backwards, but by actually treating these as sets, you can just work with equality directly. The main point is that these two quantities right here are actually equal. Phi of a commutator is equal to the commutator of the images. The book, of course, also isolates these types of results out for important use. And so I will, in their statement, of course, the problem with that is it makes their statement of their theorems a lot more technical and complicated than it needs to be. But I will point this one out because we're going to use it in a second. So the final major result is this one. So we already know subgroups of solvable groups are solvable. And quotients of solvable groups are solvable, but turns out this converse idea is also true. If you have a normal subgroup, and that normal subgroup and the quotient are both solvable, then your original group is also solvable. This is often used for inductive proofs of solvability, and we use it for two of our major theorems. And the proof. Well, you look at the derived lengths. So in other words, the nth derivative derived subgroup of n is trivial. And you look at a derived length for G mod n. The derived length, we're going to suppose it's m. And then what we're going to do is we're going to take the homomorphism from G to G mod n, the obvious trivial surjective map. And as we just noticed, the images of the ith derived subgroup is the ith derived subgroup of the image, which in this case is G mod n. So in particular, phi to the G to the m, G to the nth power, the nth derived subgroup of G mod n, which is 1, in this quotient group. And the identity element in this quotient group is 1n. So it tells you whatever these x's are, phi of x, which by definition is xn, ends up being equal to n, which shows you x is in n, which shows us that the mth derived subgroup is actually a subgroup of n. Oh, but if you take the nth derived subgroup of n, you get 1. So if we go to m plus nth derived subgroup, then we're going to get what we want. So we see that the m plus nth derived subgroup of G is actually the trivial. Well, it's a subgroup of the trivial group. And so the derived length of G is at most m plus n. So again, there's another result. This one is also, well, I'd say it's probably provable directly if you had a normal series for the subgroup and a normal series for the quotient. Well, then you use isomorphism theorems to lift the normal series from the quotient to be, and you sort of glue the two together, and you use a bunch of the isomorphism theorems to prove that you actually get a subnormal series for G that shows that G is solvable. But again, it ends up being very technical, so having this shorter proof using induction is a lot nicer. So now we're going to cover a few other theorems about solvability, some of which we'll prove, some of which we won't. But the book mentions it, so I thought I might as well. The first one we will prove is that if your group factors as a product of two prime powers, then your group is solvable. Originally I said we were going to probably skip the proof, but actually looking at the proof recently, I've decided we will cover it soon. And there's only one little technical lemma that I will state, and that lemma will be the thing that we have to wait till later in the semester to prove. But aside from one little technical lemma, the rest of the proof actually can be proven with what we already know. So you can beef up Burnside's lemma. There's a much stronger one called Phillip-Hall's theorem. It says whenever you can factor G as P to the A times M, where the GCD of M and P is 1, now this is going to be for all P dividing the order of G. Suppose there actually exists a subgroup of order M, then G is solvable. So this seems like a strange theorem, and this way of stating it doesn't quite make a whole lot of sense. What you're proving is the existence of subgroups whose index is equal to the size of a CeLO P subgroup. So they call these CeLO P complements. Notice that Burnside's theorem technically follows from Phillip-Hall's theorem because you've only got 2 primes to consider, and in both cases H would actually be the CeLO subgroup corresponding to the other prime. And so these conditions are satisfied, and so the conclusion is that G is solvable. The reason why we always state them separately is because the proof of Phillip-Hall's theorem actually requires you to use Burnside's theorem, and no one has a proof that avoids it. Finally, there's the famous Thompson theorem. This one is famous for taking 255 pages in a research journal. This is also known as the Odd Order Theorem. This should be the one that if G is odd, then it is solvable. So I've mentioned it already in the course without using the word solvable yet. But now that we have the terminology, I can state the correct version. So in the classification of finite simple groups, this is an important result because being solvable definitely means you're going to have a normal subgroup. So this tells you that all the finite simple groups have to have even order. Finally, another theorem due to Thompson is that if for all x and y and g, the subgroup generated by x and y is solvable, then G is solvable. Now, of course, this seems like a simple criterion, but it's worth pointing out you can get pretty large groups that are still generated by 2 elements. The symmetric group is a very large group that's generated by 2 elements, an end cycle and an adjacent transposition. So it's possible for some groups that this condition isn't really worthwhile, but for other groups this might be a worthwhile condition. What I mean, of course, is that if your group is actually generated by 2 elements, then this is saying that your group is solvable implies your group is solvable, which is kind of a stupid statement to make. This proof also takes hundreds of pages and relies on this theorem as well. Those who are interested might note that the textbook goes on in this section to prove the fundamental theorem of finite abelian groups directly, We're going to skip that proof because it's rather complicated and several of the steps are still skipped and left to the reader.